2022 is Professor Moreno Mejia from National University of from National Autonomous University of Mexico in Mexico, and the title of the talk is Computing Verlinde Traces. Professor Moreno Mejia, you may start, please.
Thank you, Mustafa. Okay, to talk about Verlinde traces, we have to talk about modular spaces of semi-stable vector bundles on curves. We mean vector bundles with fixed determinant. So specifically, what are these modular spaces? Well, these modular spaces are varieties that parameterize certain classes of vector bundles defined on a specific curve, the so-called semi-stable vector bundles. And in this case, they are of rank R with fixed determinant psi, and psi is a line bundle defined on the curve, and the curve is a smooth, complex projective irreducible curve denoted by X that has genus G. These modular spaces turn out to be normal projective varieties of dimension R squared minus 1 times G minus 1. And for instance, the singular locus are precisely the vector bundles that are not stable. There are some survey papers by Babil that contain a lot of information and references about this type of modular spaces of vector bundles. And also you can find there an introduction to the Verlinde formula. I will show you now the references on the screen. And you can see that the papers that I was alluding to. And the important one of the important things about these modular spaces is that their Picard group is an infinite cyclic group.
Just a question, please, Professor Moreno Mejia. You are working on the field of complex numbers, is that correct?
Yes, because one of the tools that we are using, the holomorphic Lefschetz theorem, works on the complex numbers.
Thank you very much, Professor.
The Picard group is generated by an ample line bundle, which is called the determinantal line bundle, and its global sections. The global sections of its tensor powers are called Verlinde spaces. their dimension, their dimensions can be computed by the Verlinde formula. The Verlinde formula was first discovered by physicists, and later it was and was proved by several mathematicians. For instance, in the case when phi is the trivial line bundle, it looks like the following. Well, now what we are interested in is something that we call the Verlinde traces. And what is that? To define the Verlinde traces, we need to consider some additional hypotheses. We need the curve X to have a finite automorphism group G, and we require that the line bundle psi is linearized with respect to this group G. Under these conditions, we can assume that the determinantal line bundle is G linearized, and then there is an action on the Verlinde spaces. A linear action of the group G on the Verlinde spaces. And then what we mean by the Verlinde traces, well, are traces of elements of G on these spaces, and the problem is, well, to compute these traces. Okay. So what kind of tools can we use to try to compute the Verlinde traces? As we already mentioned, the main tool is the holomorphic Lefschetz theorem. This theorem tells us how to compute Lefschetz numbers of G-linearized vector bundles defined on smooth complex projective varieties. As we know, Lefschetz numbers will not be traces, but linear combinations of traces of an automorphism on the cohomology groups of the vector bundle in question. For the theorem, we need to consider an automorphism H, the components of its fixed point set. Each component is denoted by the letter Z. And then the theorem tells us that the Lefschetz number LHE, sometimes written LHWE, is the sum of some contributions of the components of the fixed point set. Each contribution depends on some spatial data coming from the corresponding component set, namely the generalized Chern character, something called the stable characteristic classes, and the Todd class, which is more or less standard, and this special determinant. Well, this theorem works on smooth varieties. However, our variety is not always smooth, and in the non-smooth case, one could use the Lefschetz-Riemann-Roch theorem for singular varieties, and by doing so, one would obtain directly the Verlinde traces because of the vanishing of the higher cohomology groups of the positive tensor powers of the determinantal line bundle. Those would be the tools that one could use to try to compute the Verlinde traces. Okay, although using the Lefschetz-Riemann-Roch theorem for singular varieties would be a more direct approach to our problem, we do not follow that path in our work. Anyway, this approach is of course interesting, and it has already been addressed in the work of J. Anderson, and the title of his work is The Witten-Reshetikhin-Chiraev Invariance of Finite Order Mapping Theory 1. And that's where one can have a look at this approach. Okay. For the holomorphic Lefschetz theorem, we cannot use it directly because the moduli spaces have singularities. So what can we do to compute these Verlinde traces then? So there is the Jacobian approach, and this is based on this isomorphism. So the these Verlinde spaces, this is just the first power of the determinantal line bundle. The global sections of the determinantal line bundle are isomorphic to the dual of the global sections of the R theta divisor of the Jacobian of line bundles of degree G minus 1. That is the space of R theta functions. And so in this case, one can try to compute the Verlinde traces by computing the traces on the space of theta functions, the Jacobian. And how can one do that? Well, one considers the following exact sequence induced by the inclusion of the theta divisor in the Jacobian. And since by the Kodaira vanishing theorem, the higher cohomology groups of the theta line bundle vanish, one can write the n plus 1 theta functions, the space of theta functions as a direct sum of these other two spaces. One is other space of theta functions, and the other one is the space of the global sections of the theta line bundle restricted to the theta divisor. Okay, then now one have to notice that if one can compute the traces on the space of the global sections of the theta line bundle restricted to the theta divisor, then one can compute the Verlinde traces. One can compute these traces here by induction. In this case, this space this space can be identified with the global sections of the powers of the canonical line bundle of the symmetric product of the curve because of the Abel-Jacobi map. This symmetric product is birational to the theta divisor, and one can prove that these spaces are canonically isomorphic. And I computed those traces a long time ago by using the holomorphic Lefschetz theorem on these spaces. Okay. So this is one approach, but this does not allow us to compute all the Verlinde traces because we can compute Verlinde traces only for the first power of the determinantal line bundle. So one has to have a look at how other people computed the Verlinde formulas, and in particular we look at the method that was used by Thaddeus. So for this approach, we will assume that the curve is embedded in a projective space via this linear system, this complete linear system, which is this is the canonical line bundle of the curve tensor with our line bundle psi. And then then one needs to define some line bundles, which we call not line bundles, the vector bundles on the symmetric products of the curve. And, we call them the Thaddeus bundles. One is this WI minus, WI plus, and then we consider the Euler characters of these of some special vector bundle. This bundle is defined. This is another of the Tadeusz bundles, and is defined like in terms of the other Tadeusz bundles by the following formula. And then, okay, in terms of this Chern, no, these Euler characters, Tadeusz was able to compute the Verlinde numbers using the following formula. So it is a linear combination of the Euler characters of these vector bundles and the symmetric products. And then, this is a formula for not just for Verlinde numbers, it's for other numbers that we call the Tadeusz numbers. But the Verlinde the Verlinde spaces are particular cases of these spaces. So for particular values of m and n, we obtain the Verlinde spaces. So this gives us Verlinde. This formula gives us, in particular, the Verlinde numbers, and and when we add the hypothesis that the curve has automorphism group G, and that the psi is G linearized, there is some information missing here. So this implies that the Tadeusz bundles are linearized, and one has that these Tadeusz traces can be computed by a formula similar to the one of Tadeusz. In this case, these numbers are given by the following Lefschetz numbers. The Lefschetz numbers of the Tadeusz bundles P, I, M, N that we show before. Well, when I is equal to 0, we need to define a special numbers, and this is the second approach that works then for that works now for the rank 2 case, and arbitrary powers of the determinantal line bundle. Here I'm using the notation theta because the determinantal line bundle is also called the generalized theta divisor. Then so using the Tadeusz approach, we as we have to work on just on symmetric products of the curve, we can it is possible then to compute these Lefschetz numbers, and then we can compute the Verlinde traces. All we have to do is to compute these intersection numbers for each component of the fixed point set. And the fixed point sets, I had studied them in when I computed the traces on the space of theta functions, and in this work we focused on determining all the data required to compute these contributions. And so we derived some formulas to compute the contributions of the components of the fixed point set. For instance, each component depends on some invariant divisor D. Some constants that depend on the divisor are involved in the formula, which is rather a generating function, and we use it depending on what power of the determinantal line bundle are using to compute the trace. The formula also involves some cohomology classes of the symmetric products of the quotient curve X quotient with the group generated by the automorphism H. And there are some constants which depend on the particular situation. The particular situation is the curve, the automorphism, and the line bundle psi. And we compute those constants. In particular, when X is a hyperelliptic curve of genus G, H is the hyperelliptic involution, and psi is the square of the canonical line bundle of the curve. And this is the composition of this direct image into eigenspaces. This is the line bundle where the action of H on the fibers is multiplication by nu to the j, nu to the j, where nu is if the order of H is P. Then we compute this for the for a hyperelliptic curve of genus G, and when psi is the square of the canonical line bundle, then one has these values. These are other constants that are also required, and then we use them to compute the Verlinde traces for the involution of a hyperelliptic curve of genus 2.